let's get started. So I will give the floor to Peter Dowd, the IAMG president, to introduce the 2022 distinguished lecturer, Qiuming Cheng, who unfortunately had to remain in China because of a sanitary crisis.
All right, this is a virtual introduction then, given that Qiuming Cheng can't be with us in person. Professor Qiuming Cheng is an internationally recognized leader in mathematical geosciences. His pioneering research on the new fractal density theory and nonlinear mathematical models for singularity analysis have made major impacts on several geoscientific disciplines, including those concerned with extreme geological events originating from nonlinear processes of plate tectonics, such as formation of supercontinents, magnetism, mid-ocean ridge heat flow, earthquakes, and mineralization. His multifractal filtering and singularity analysis techniques are now routinely applied for anomaly identification in mineral exploration and in environmental assessment. Professor Cheng has received several prestigious awards, including the William Christian Combine Medal, the highest award bestowed by the IAMG, the National Science and Technology Progress Award awarded by the Chinese government, and the AAG Gold Medal, the highest award bestowed by the International Association of Applied Geochemists. Professor Cheng served as Associate Editor for Computers and Geosciences and the Journal of Exploration Geochemistry. Professor Cheng co-chaired 2 IAMG annual conferences, one in Toronto and the other in Beijing, and he served as President of the IAMG, President of the International Union of Geological Sciences, and a member of the Committee of the Science for Planning International Science. Professor Cheng was elected a member of the Chinese Academy of Sciences in 2019 and a foreign member of the Academia European in 2020. He is now a professor at the School of Earth Sciences and Engineering at Sun Yat-Sen University. And I think we're ready to go with the
Good morning, everybody. This is Qiuming and Chen from China. First, I apologize for not being able to come to France to attend the meeting in person. It is said that the COVID-19 has affected our life for almost 3 years now. First, I'd like to thank Professor Qiuming for the invitation. I also like to thank the entire organizing committee of IAMG 2022 for their effort to make this year's conference happening. And it is my great honor to give this keynote lecture as the IAMG distinguished lecturer today. I'd like to thank Professor Peter Dowd, the president of IAMG, and the entire IAMG council for the support. I also like to thank Professor Christine Todd and her team of the Distinguished Lecture Committee for choosing me as the candidate of the DL of this year. So the title of my talk for today is Quantitative Simulation and Prediction of Extreme Geological Events. Before my talk, I'd like to acknowledge the following organizations, the programs for their support. First, I thank IUGS-EC. And this year, the IUGS is celebrating its 60th anniversary. Thanks are due to UNESCO for establishing the UNESCO Chair on Deep Time Digital Earth and Mineral Resources. Once again, I'd like to thank IAMG for choosing me as the Distinguished Lecturer of the Year. As the initiator of the IUGS Big Science Program, I'd like to thank the Deep Time Digital Earth team. I'd also like to thank the China Natural Science Foundation for providing research grant. Last but not least, I'd like to thank my universities, my colleagues, and my students. So for the IAMG Distinguished Lecture Tour in this year, I have prepared several topics, as you can see on the screen. These topics were also included in a note published in one of the issues in IAMG newsletter. I keep open for comments and suggestions about where and what I should deliver during the tour. And so I hope, you can give comments and suggestions. And also, I appreciate if you could spread this information to your students, colleagues, and friends in case there are interest, and so they can communicate with me. Thank you. So for this talk, I'd like to first briefly discuss about the complexity of extreme geological events that include what is a extreme geological event and what is the key property of a extreme geological event. And the second, I wanted to introduce the recent development of mathematical theories about fractal density and local singularity analysis type of techniques. And then finally, I want to introduce a few case studies to show how these techniques can be applied for simulation and prediction of extreme geological events. So this slide shows that the major and extreme geological events occurred during the evolution of the Earth, that they indeed shape and transform our Earth, as well as form environments and life of Earth, especially the resources, energy. So this systematic study of extreme geological events, it is important not only for understanding the abrupt changes in the evolution of the Earth, but also for an in-depth understanding of the co-evolution of the Earth's materials, including resources, energy, Earth's life, and how the Earth's environment changes through time. And there are many types of geological events or X events or occurred in different fields. The X events means those small or large events occurred in limited space and time intervals, but their amplitude somehow beyond normal threshold. And the events are in lower occurrence frequencies, but with a high impact, either for resources, energy, or cost hazards. Further check into the various types of events occurred along the boundaries of the plates caused by plate tectonics. This X events depict several types of nonlinear processes, such as intermittency, avalanches, and singularities that are physically corresponded to the mechanisms of phase succession, self-organized criticality, and the multiplicative cascaded processes, including chaos. So the fundamental laws related to these processes is the outcomes with parallel relations that associate the variables with self-similarity, scale invariance, and singularity. So in order to study X events, we need to define what is the X event and what is the key features or characteristics of X events. So we need to define measurable variables to describe X events. Our studies about the various types of extreme geological events indicated that most of the X events depict a nonlinear property, that is, the mass density or energy density caused by X events are undifferentiable, which means the density can approach to either zero or infinity when the measuring scale approach to infinity small. For example, the mass density of metal within a volume of ores can be represented as the ratio of mass over the volume, which when the volume approaches to zero, the density can approach to infinity. So similarly for the earthquakes as shown in the middle, the seismogram indicates that within a very short period of time, an earthquake can release a huge amount of energy. If we use the ratio of energy over the time duration, then energy density approaches to infinity when the time reduced to zero. The third example on the right is the case of heat flow released at the mid-ocean ridges where the plate is spread apart and high heat flux approaches to infinity when towards the edge, the ridge axis. Therefore, we can define X events are those events that can cause singular density indicating anomalous amount of mass concentration or depletion, or anomalous release of energy or absorption of energy within a small space or interval. So the second part of the talk is about the concept and methodology developed for handling the divergence of the density and the complexity of geological events. This includes fractal density and local singularity analysis. As we know, fractal scales and self-organized criticality, etc., are newly developed math physics in the past 50 years that describe geocomplexity as a new science. In the IAMG field, there are a growing number of researchers, especially young people who are interested in the topic and conducting research along these lines. For those of you who are not familiar with these topics, fractals refers to geometries with fractal dimension. The dimension could be non-integer values, such as the dimension of Koch curve, which is a fractal, and the dimension is about 1.26. So the geometries between the regular point and line area and the volumes are irregular geometries with fractal dimensions. So this type of geometries need to be measured in the fractal dimensional space. Otherwise, their size becomes either zero or infinity. For example, for the coastline type of lines, their length as measured as lines is infinity, but their areas measured as 2D object become zero. So this type of fractals need to be measured in the relevant fractal dimensional space in order to get their size. To explain briefly about the complexity, I'd like to use this slide and also to demonstrate why fractal geometries have complexity. In my view, if a geometry cannot be quantified by the traditional method, or if a physical property cannot be quantified by traditional physical parameter, meaning that they do have complexity. Take a line example for linear line, nonlinear but smooth curve. We can use traditional ruler method to calculate their length. That is to use the total number of rulers multiplied by the size of the ruler unit, and then we can calculate the length. But for Koch curve, like fractal curve, we cannot use the same method to calculate length. For example, if you use the total number of rulers multiplied by the size of rulers, then the values will approach to infinity when the rulers become infinitely small. Let's look at the mass density of fractals as type of measures defined on support of fractals. The traditional mass density is the ratio of mass over the volume.
But when consider fractals such as Menger sponge, which involves connected voids, which leaves its volume becomes zero, so that any mass density defined on these fractals become infinity. However, if we extended the density from the simple ratio of mass over the volume to the mass over the size of fractals measured in fractal dimensional space, the density will become a constant. Of course, the fractal density with the unit of mass over the size of fractals. And the difference between the fractal dimension and its Euclidean dimension indicate the degree of fractality. And this value is also termed the singularity index, which is very useful parameter I will show later on for application. Based on this concept, we can extend the traditional calculus to fractal calculus. For example, we can change the measuring unit of integrals and differential operations to the unit of a fractal dimension. So I don't have time to go through the details of this operation. And this fractal density concept and operations, we can apply them to characterize extreme geological events, as I will introduce in the next few slides. So the next part, I will show several case studies of X events. So I'm going to show three types of applications of fractal density in the local singularity analysis method. This includes, in the first example, where fractal density can be used as a parameter or an attribute in dynamic systems for predicting the heat flux and the floor depth over the mid-ocean ranges. In a second type of application, the singularity index is to be calculated and used as high-pass filtering to analyze the time series data, especially for deep time geological time series data. And in the third type of application, it involves mapping the singularities to support predictions for mineral deposits and field mineral expression and environmental impact assessment. In the case one, it's about modeling heat flow and floor depths over the mid-ocean ranges. Plate thermal-conductive models have been developed for estimating heat flow and floor depths over the mid-ocean ranges in the 60s. It was an important topic for plate tectonics at that time. And this model assumes the thickness of the lithosphere, like alpha, and the density, velocity, temperature at the bottom of lithosphere, like T1, and the temperature at the surface of ocean floors, like T0. It also assumes the spreading rate of plate is V. And so given this, of course, other parameters like thermal diffusivity and heat capacity, etc. And based on these parameters, a conductive models can be established which give approximate solutions for predicting the heat flows and the floor depths at the distance from the axis, or as increase the age of the lithosphere. The distance is equal to the age of the lithosphere multiplied by the velocity of half plate spreading. Based on this assumption and the parameters, one can derive the theoretical solutions. So on the right lower corner, the graph shows the theoretical curve versus the observed curve. So people found the theoretical curve could not predict the heat flow over a very young lithosphere, and also the models does not fit the floor depths well for old age lithospheres. This leaves a long-standing question about what causes these problems. Considering the problems of the solutions do not fit the data well for young lithosphere age, so two functions were suggested to do the prediction. For a young age, let's say less than 55 million years, the authors suggest to use a power law function with the 0.5 as exponent or square root of t. But for old age, like say beyond 55 million years, they use exponential function. I substitute the ordinary density with fractal density of lithospheres and reproduce the consecutive model, which gives the two solutions both in a power law forms with two terms added to the old solutions. These two modifications include a time to the power of half of the singularity, and the second factor is a constant associated with a plate spread velocity. So these new solutions fit the heat flow data and flow depths well throughout the entire age range. The second examples I want to introduce is a research I did on analyzing global tetrato zircon, uranium lead age data, and other isotope data to study the episodical or periodical evolution of Earth's continent. The values and the frequency distribution of the isotope age from tetrato zircons show episodic sharp peaks of frequency distributions, which generally correspond to so-called non-aggregation of supercontinents. The lower graph shows that the age peaks from continent magmatic data and age data from the ocean basalt shows correlation, which means that the major magmatic events are mantle-rooted and represent real and major magmatic events. The question is that are the magnitude of these peaks meaningful, and can we extract any more information about the evolution of the continent from the data? There are 5 global data sets available for the study at that time. This is the 5 data sets. For these 5 global databases, I use the singularity analysis method to process the time series. At the bottom graph, you can see the curve indicates the singularities calculated from the time series give the properties that the frequencies of the curve is increasing, but the magnitude of the curves decreasing. And considering the mantle temperature decreasing, and we set extrapolated models to predict in the future 1.45 billion years should be the minimum age of the plate tectonics activity. So the third example I wanted to show here is about a research conducted by my group in collaboration with colleagues from Queen's University of Canada and the University of Wisconsin. The study is based on a database from Microstrata, which is a data platform created by Professor Shana Peters' team in University of Wisconsin. It uses a GIS polygons, GIS techniques to create polygons around stratigraphic sections and they form a columns to read the data from publications. The platform uses supercomputers and machine reading techniques to extract geological data relevant to the spatial and temporal distribution of sedimentary, igneous, and metamorphic rocks, as well as data extracted from them. And the platform provides different type of outcomes, including time series dataset for supporting relevant studies. For example, on the right, the lower corner, that curve shows the North America net sediment in cellular marine environment.
In this study, we used the marine sediment flux data series as shown on the lower left of the slide, which include about 21,000 sedimentary rock units from about 1,000 composite regional geological columns. Temporal variations in the surviving sediment abundance reflect the combined effect of a gain and the loss of the sediments due to the net sediment accumulation. This can be represented as a time-integrated probability of erosion of the continent and destruction of sediment, for example, due to plate subduction. The local singularity analysis method was applied to process the time series data. The processed results of sediment flux singularity clearly show a remarkable cyclicity of the sedimentary record and association with the separation and aggregation of a supercontinent. For example, the lower anomalies of intensity of sediment flux measured by the singularity, as shown in the middle graph, are temporarily associated with the aggregation of supercontinents. This discovery supports the hypothesis of sediment may act as lubrication to promote plate subduction, resulting in a loss of sediment flux. So this example is about a research on reconstructing atmospheric oxygenation history. According to the literature, 3 levels of oxygenation of Earth's atmosphere are associated with 2 great oxygenation events, so-called GOE and NOE. GOE was happened around 2.5 billion years, and the NOE was occurred in around 0.5 billion years. Therefore, to reconstruct high-resolution oxygenation history is an essential task for quantitative studies. In this study, we use a database so-called EarthCam. So the EarthCam portal is an online service enabling simultaneous search of federated databases of various kinds and access to geochemical and geochronological data for about 300,000 rock samples covering almost every continent and spanning the entire Earth's history. From the graph on the left side, you can see the locations of the samples, and the middle graph showing the changes, some of the values through time, and the right is a paper published in 2012 in Nature about the discovery of the change of mafic geochemical data through time, especially around the GOE, the Great Oxidation Event. This study tried to couple the mafic igneous geochemical evolution and atmospheric oxygen. And we use the mafic igneous geochemical data from batholiths and processed by 3 techniques. They are self-organized mapping, principal component analysis, and regression. SOM and PCA were used as unsupervised method for classification, and regression was used to associate the PCA scores to the values of oxygen, and the model of regression was used to predict or to reconstruct the Earth's oxygen curve. In the middle of the slide, on the top, that is the graph showing 4 clusters generated by SOM method. And so those 4 clusters showing kind of similarities with the 3 level of oxygen change through time. And the lower graph show the PCA scores, and they are associated with the quantitative value of oxygen through time. In this slide, you can see at the bottom graph where the red dots connected by blue curve represent the predicted result of oxygenation or oxygen curve by use this regression method. What you can see is that this result gives kind of variabilities of the predicted oxygen curve, especially during that so-called Borebillion period, that is from 2.5 to 0.5 billion years. So this result indicates that the agreement with independent proxy predictions from the literature based on sedimentary data and the prediction result from this study based on mafic igneous data implies that the Earth's oxygenated atmosphere may be at least partially a natural consequence of mantle cooling, and especially that involving mantle melts collectively helped modulate the balance of the early oxygen sources and sinks. This result has just been accepted by a Natural Communication journal.
The last example is about the application of a mapping singularity of geochemical data for predicting location of a mineral deposit. Fractal future techniques based on spectral energy fractal density SA model was applied to map local anomalies of streams geochemical data in the Lanping Jingdian Mineral District in Yunnan Province, southwestern China. Maps were created based on stream sample data, the values of zinc and lead in stream sediments are influenced by rock types, especially the Alosan basalt that has high concentration of lead and zinc and other elements. It is usually difficult to separate anomalies caused by lead and zinc mineralization from the high background caused by volcanic rocks. The SA fractal filtering method was applied to the map of zinc and lead and other elements, which reduced and detrended the data and enhanced the anomalies. The results of target areas, like delineated by the method, eventually led to several new discoveries of mineral deposit at that time. So this type of fractal filtering techniques has become a common method for processing geochemical data in the field of applied geochemistry.
The above case studies shows evolutions of Earth's tectonics, atmosphere oxygenation, and marine sediment flux through time. The results include a refined reconstruction of the atmosphere oxygen history using machine learning techniques on the basis of basalt geochemical data. Singularity analysis methods were used for processing time series data related to metamorphic activities and marine sediment flux. The results revealed that both magmatic flux and sediment flux depicting secular trends that are associated with aggregation of supercontinent. We have also done a bit of work about biodiversity through time, but I did not have time to go through it. These results provide a base for further studies of co-evolution of Earth's environments, Earth's life, and Earth's materials, including useful minerals and mineral resources.
As conclusions, I'd like to make a few remarks. First, fractal density is a generalized form of traditional density, and it describes density with fractal dimension or density measured in fractal space. Fractal density is a common property of extreme geological events originated from plate tectonics due to phase transition, self-organized criticality, and a multiplicative cascade process, including chaos. Local singularity analysis type of techniques can be used for three types of applications: new parameters and attribute in dynamic models, high-pass filtering techniques, and singularity mappings for predictive purposes. Thank you for your attention. Thank you.
Thanks a lot, Qiuming. So, are you online? Yes. Okay.
Hello.
Hello. Hi.
Can you see me?
Yeah, we see you and we hear you. Excellent. Technology is working.
Finally. Oh,
Very
thank
good.
you so much.
Very good. Thanks very much for the excellent talk. Any question for the from the audience? No questions. Oh, Gerald?
I would still like to understand how you measure this fractal density in a practical situation with finite resolution. So I know it's a stupid question, but I'm interested.
No, I think it's an excellent question, actually. Can you hear me, right?
Yes.
Yeah, I think. I mean, this is an excellent question because with the concept, we need to have practical method to calculate the values in order to really use it as either index or attribute for those three type of applications. Of course, not only three type of questions, but application, but. Yeah, so for example, for 1D time series kind of data, I can set the time, and then I can use the different time intervals centered at that given point of interest. Usually that is where you have a singularity, and then I can change the size or duration of the time. And then to calculate, for example, what is the total values or energy or mass, and against the size of the interval, and then I can plot the size of the time interval against the total value in a log scale graph. So that will give you the slope is the singularity, and then the intercept is can be converted back to that fractal density. Yeah.
Okay.
Yeah, that's for 1D. For 2D, of course, it's as a map. You can use windows of different kinds and different sizes and calculate the values. And then in that case, the values against the area. Similarly for 3Ds.
Thank you. We have another question.
Thank you for your very nice talk. I'm curious if you already used a technique called Detrended Fluctuation Analysis, DFA. Have you heard about it or have you used it?
Yeah, actually, we use a little bit. Like one of my PhD students did a study of using that. Yes, it's another technique. It's a sophisticated technique, yeah.
Okay. Okay, what is the probability of an extreme event we experience today, like having the video projector breaking down and then the sun breaking down? No, it was just a joke, sorry.
Hi, Qiuming. Thanks for the very nice presentation. I wanted to follow up a little bit on the previous question, since there are a number of available techniques for calculating fractal exponents. And for example, a method such as DFA can also remove trends from the time series and therefore just focus on the exponent that would describe the behavior of the fluctuations. So I was wondering if in your approach you somehow remove possible trends or you use the entire signal to calculate the fractal exponent.
Yeah, that's a good suggestion, actually. Yeah, thank you for the question. And yeah, so there are a number of techniques actually to do this, and there are similarities or differences. I think the similarities are all remove the trends and to calculate the local variability. And so in that case, they all can do the trending, or remove the variable background. But the difference is that some techniques, for example, we can use also wavelets, the kernel kind of windows. In that case, is more smooth or sophisticated. But yeah. So we can use different techniques. But to demonstrate the simple principle, I use a very simple one. That is to use the average of values within the area or segment. So, but we could use other techniques as well.
Okay. Thanks again, Qiuming.
Thank you so much. It is a pity that I could not be there in person, and feel sad about it, and apologize for not being able to go. And not only for myself, but for a whole group from China, from mainland China, we cannot be there. Sorry about that.
Thank you.
I'm going to miss you all.
Thank you. And I think we are going to have, please stay with us, we are going to have a virtual
coffee break
ceremony. So Peter. And I guess if you stay here, at least we will have a picture somehow.
Okay. Hi, Peter. I feel really ashamed not be able to see you or see others on site. Yeah, apologize for that.
Well, here is your certificate, and it will be in the post. Congratulations. This way.
Thank you. Thank you so much. Thank you.
Thanks a lot, Qiuming. Congratulations.